Nuclear fusion is the opposite of nuclear fission, and so is the joining together of two or more atomic nuclei into a single, heavy atomic nucleus, releasing subatomic particles such as neutrons, neutrinos, antineutrinos, electrons and positrons as byproducts in the process. Fusion requires extreme conditions, high temperatures and pressures, in order to occur. This is because for the nuclei to fuse, the repulsive electrostatic force that exists between the multiple nuclei, all being positively charged, must be overcome. The nuclear force, the force that keeps nucleons together, is stronger than the electromagnetic force, and so can overcome this electrostatic repulsion between the nuclei. However, the nuclear force has a very short range, on the order of a diameter of a nucleon. Therefore, only when the temperature is hot enough, or alternatively the pressure is high enough, can the nuclei get close enough to one another so that the nuclear force overcomes the electrostatic repulsion, fusing the nuclei together. Quantum tunneling, a quantum physics phenomenon where a particle has a small chance of tunneling through an energy barrier even though it does not have enough energy, according to classical physics, to overcome it, helps to slightly lower the energy requirement. This is because it means that some particles will be able to tunnel through the remaining energy barrier when the temperature is nearly high enough for all atoms to fuse. Even ignoring the large energy requirements to make fusion happen, fusion of some elements absorbs energy. This is due to the nuclear binding energy of the atoms involved in the process. Nuclear binding energy is the energy required to break a nucleus into its constituent parts. It can be worked out by finding the mass defect within the nuclei, using Einstein's famous equation E equals mc squared. Basically put, an increase in nuclear binding energy will release energy, while a decrease in nuclear binding energy will absorb energy. When the binding energy per nucleon is plotted against the mass number of the element, you get what is known as the nuclear binding energy curve, which is shown on the screen. As you can see, generally fusion between elements smaller than iron 56 releases energy, while fusion of elements above iron 56 absorbs energy. Knowing the nuclear binding energies of the nuclei involved in the process allows you to work out exactly how much energy will be released or absorbed in each individual reaction. The energy released by fusion is in the form of heat. When fusion does release energy, it releases much more energy than was required to overcome the electrostatic repulsion between the nuclei. This means that the fusion reactions can be self-sustaining, meaning no external energy input is required to keep the reaction going. When a reaction has reached this point, it is known as ignition. Nuclear fusion is currently being developed for use in power stations on Earth. Fusion could provide cheap, green, and safe energy, and so there is a vested interest in developing fusion energy. Fusion is safe because, unlike in fission reactors, there will only be a very small amount, about 1/10 of a gram, of fusion fuel contained in the reactor at one time, and so the reactions can be easily halted by stopping the injection of fuel. The main fusion reaction that researchers are targeting, simply because it is the easiest, is the fusing of deuterium, hydrogen 2, proton with 1 neutron, with tritium, hydrogen 3, proton with 2 neutrons, to form helium 4. Due to the many technological hurdles needed to be overcome, process in developing fusion energy has been slow. However, recently, researchers at the Nuclear Ignition Facility, NIF, in California, USA, have been able to get more energy out of the reaction than was put in, which is a vital stepping stone on the road to achieving ignition. The NIF adopts one of the two major approaches to fusion, inertial confinement. This is where powerful lasers or ion beams are used to rapidly implode a shell, which then contains and heats the plasma, which is the fusion fuels, in an ionized gaseous form. The other approach is the one that the Joint European Torus, JET, based at the Clements Centre for Fusion Energy in Oxfordshire, adopts. This is magnetic confinement, where strong magnetic fields are used to confine the plasma within a vacuum so that the plasma does not lose heat by touching the walls of the reactor. The plasma can then be heated by external sources. The successor to the JET will be ITER, which is under construction in South France and is being funded by countries around the world. This is planned to be the last experimental fusion facility of its kind, before it is hoped that by the mid-century the first prototype commercial fusion power station will have been built. The method that stars achieve and sustain fusion by is through gravitational confinement. This, however, cannot happen on Earth because there is simply not enough matter to create a strong enough gravitational field. The first fusion reaction that was achieved on Earth was in 1949 in the form of a hydrogen bomb. Here, the energy released from nuclear fission is used to create an uncontrolled and unconfined fusion chain reaction. Stars are formed within nebulae, which are interstellar clouds of gas and dust. If the mass of a cloud is larger than a certain limit, known as the Jeans mass, the cloud will collapse under its own gravity into a denser ball of gas. The process continues until the ball of gas becomes so dense that it is opaque to its own radiation. Photons bounce around inside the ball of gas, raising its internal temperature and pressure until the point where they can balance gravity. The clump of gas, however, still contracts gently under gravity. The clump of gas is known as a protostar. After about 30 million years for a ball of gas of similar mass to our Sun, of gentle contraction under gravity, the centre of the clump becomes hot enough and of high enough pressure to start the fusing of hydrogen, the beginning of the proton-proton fusion chain. For stars about 1.3 times heavier than the Sun, the CNO fusion cycle is the main source of energy. The energy released by nuclear fusion prevents further gravitational contraction. The star is now in its main sequence phase. The evolution of a star and the amount of time it stays bright for depend mostly on its mass and only partly on its composition. Lighter stars burn for longer, while larger stars burn out in much quicker time frames. As the star runs out of hydrogen to fuse, it begins to contract due to the lack of outward pressure from nuclear fusion. The contraction stops either when the electron degeneracy pressure, see screen, becomes sufficient to oppose gravitational collapse, or the core becomes hot enough, around 100 million Kelvin, for the triple alpha fusion process to begin. Stars from around a half to 10 times the mass of the Sun will become red giant stars after their main sequence phase. A layer of hydrogen surrounds the core filled with helium. The increased brightness and size of a red giant star is due to this hydrogen being fused at a quicker rate. Then once the central helium is used up, fusion of helium and hydrogen respectively will continue at an ever-increasing rate in shells surrounding a hot core of carbon and oxygen. Eventually, these outer layers will be ejected, forming a planetary nebula and exposing the core of the star. The remaining core of the star will then cool before becoming a white dwarf. White dwarfs will eventually run out of energy, and all that will be left is a cold, dark mass known as a black dwarf. However, the universe is not yet old enough for any black dwarfs to exist. Stars much bigger than the Sun follow a different evolutionary path. These stars form red supergiants after the end of their main sequence phase. The star will continue to fuse successively heavy elements till it arrives at iron 56. Here, the electron degeneracy pressure will become insufficient to support the star's weight against the force of gravity, causing a gravitational collapse. This can cause the violent expulsion of the outermost layers of the star in what is known as a supernova. What is left of the core of the star will have either become a neutron star or a black hole. Neutron stars are extremely small and dense balls of neutrons and protons, which are the main survivors of the collapsed stellar core. These stars resist further gravitational collapse through neutron degeneracy pressure, see screen. However, if the mass of a stellar remnant, remains of the collapsed stellar core, is high enough, the neutron degeneracy pressure will be insufficient to prevent further gravitational collapse below the Schwarzschild radius, see screen. Thus, a black hole forms from which strictly nothing, not even light, can escape once past the event horizon. Shortly after the Big Bang, a process called nucleosynthesis ensued. Nucleosynthesis is the joining together of nucleons to form nuclei. Around 3 minutes after the Big Bang, When the universe had cooled sufficiently, hydrogen-1 protium began to form deuterium before that in turn fused to form helium-4. In this phase, very small amounts of lithium-7 and of the radioactive isotopes tritium and beryllium-7 were formed. Elements up to iron 56 are formed in stars through nuclear fusion. This is known as stellar nucleosynthesis. Elements above iron 56 are formed in supernova explosions through both nuclear fusion and a process called neutron capture. Neutron capture plays a primary role in the production of elements above nickel. Neutron capture is where an atomic nucleus collides with one or more neutrons to form a heavier nucleus. The process often involves beta decay. This is not the same as nuclear fusion. The main neutron capture process that takes place in supernova nucleosynthesis is known as R process, R for rapid. Slow neutron capture process, or S process, S for slow, can happen in stars of similar size to our Sun and can create elements as large as bismuth 209. We and everything we see around us were made in stars that ended their days billions of years ago.